Directional couplers can split or combine the signal, and in general, the number of input ports is not equal to the number of output ports. For example, a directional coupler 1 to n shows here there is only a single input port that splits light to m output ports. For ideal coupler, the optical power will split equally between all output ports. Or we can reverse the situation and send light. We have a number n of input ports and only one output ports. It means that signal from any of the input ports will go to output port. In general, for any passive directional coupler, we can have a number of input ports. Here it shows as n ports, and a number of output ports. Here it shows as m output ports. And again, the number of input ports does not have to be the same as the number of output ports. So from the signal incoming to any of the input ports will ideally split equally between all output ports. There are several techniques how to make directional couplers, and three techniques we will discuss in the next several slides. They fiber fusion, evanescent coupling, and beam splitting. So how to make a directional coupler by fiber fusion? The fused biconically tapered directional couplers can be made by twisting two bare fibers around each other, then heating the junction until the glass softens, and then pull the fiber ends apart, pulling it apart and forming a taper in the fused portion of the coupler. And this process of making couplers by fiber fusion is shown schematically on this slide. Again, first fibers, two bare fibers are twisted around each other, then we heat the junction until the glass softens of this twisted area, and then we pull fibers ends apart, forming a taper in the fused portion of the coupler. Second method is evanescent coupling. Evanescent coupling works only for single mode fibers. It will not work for multi-mode fibers. So for single mode fibers, it is based on bringing two fiber cores close to each other by sharing its cladding, so producing a coupling between two fibers in this area where two cores of the fibers are very close to each other, so it's possible to couple energy, optical energy from one fiber to another by evanescent field. That's why it's called evanescent coupling. So what happens if there is no coupling and we start, for example, in the first fiber, the light will continue in the same fiber. But when we have effective coupling, it is possible in principle to decouple light from the first fiber and couple it 100% to the second fiber. And bottom part shows schematically this principle. So it is 2x2 directional coupler. We have two ports on the left and two ports on the right, and normally port 1 is served for input, and there are two output ports, port 2 and port 3, and as before, the port where most of the light will continue is called throughput port, and the other port is called tap port. For evanescent coupling, how to bring two fiber cores close to each other? Well, there are several techniques. It could be done by, for example, fusion tapering of single mode fibers, but also we can polish part of the cladding of each of the fibers and bring them together as shown on this picture. So we removed part of the cladding and it made two cores to be close, and it's called D-fiber, polished dissection type of the coupling. Another possibility is to fabricate two cores close to each other from the very beginning and to have a twin core fiber. In this case, what's important, the distance between two cores that guide light inside the fiber is small enough to allow for evanescent coupling between optical fields in two fibers. And the last technique to make directional coupler is beam splitting. Beam splitting technique could be achieved by simply making optical setup, where what is shown schematically here. In the middle we have a beam splitter, splitting light 50-50. And let's say we have 4 fibers, labeled 1 through 4. And after the fiber, attached to the fiber is a lens. It could be a graded index lens as depicted here, or a simple aspheric lens collimating the light. So light emitted from the fiber will be collimated and continue to the beam splitter. At the beam splitter, it will be split 50-50 between two ports. For example, if we start with light fiber 1, then it will partially continue to port 3 down, because we need to consider this interface semi-transparent. Reflected light will continue to port 3 and transmitted light will continue to port 2. If we start, for example, in port 2, the light will continue and be partially reflected to port 4 and partially transmitted to port 1. If we start, for example, from port 3, the light will be partially reflected to port 1 and partially transmitted to port 4. This way we can effectively, by utilizing simple optics, to build a directional coupler. So that meaning that what is the main objective, what is the main purpose of directional coupler, is to redistribute light incoming to any of the input ports to a number of output ports. That is all for this lecture.